So we're looking at this patterned fabric and trying to figure out number of shaded squares and total shaded squares as we go, like go down the rows. So it says there are 5 shaded squares in row 3. The total of the shaded squares up to and including row 3 is 9. Remember, rows are sideways, by the way. Okay. So row 2, how many shaded squares? 3. How many total? 4. Good. Row 4, how many shaded squares? 7. And total?
16.
Okay. Row 5.
9.
And?
25.
Okay. So part B says, what number patterns do you see in the rows of the table? So rows again, sideways. Yeah, Jack.
I think it's actually Pythagorean theorem because, like, the amount of total number of shaded squares total in row 1 plus the number of shaded squares just in row 2 equivalent to the total number in row 2, then like total number in row 2 plus row number in 3 equals the total number in 3, etc.
I think you might be meaning columns. Are you meaning this way?
No, not like in the graph or like in the table.
We don't have a graph. This is called a table.
Or like in the model.
Oh, and in the actual fabric?
Yeah.
Oh, okay. All right, now we're all on board. Can you say it again?
So like 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16, 16 plus 9 is 25.
Okay, gotcha. At least we were looking in the right place. So Pythagorean theorem, just to clarify, is this kind of relationship. So,
Oh, is that the one with the triangles?
yep,
Oh,
with the side lengths specifically the side lengths in a right triangle.
Oh,
Yep.
I'm thinking the one where like number 3 equals number 1 and number 2.
Yeah, so this is what he's talking about. Okay. So basically the pattern here he's saying it looks like this. I'm pretty sure this is the one you're talking about.
Yeah.
You add like this one, you just bring down the 1. And then after that row, you add the 2 above it. So it's 1 and then 2, like 1 plus 1 is 2 and then 1. And then 1, add the 2. So that's 1 plus 2 is 3, 2 plus 1 is 3, and bring your 1 down. And then same thing, bring a 1, and then 1 plus 3 is 4, 3, 3 is 6, 3, 1 is 4, and 1. Okay? Anybody know the name of that? Fibonacci.
Oh, the Fibonacci sequence.
Have you ever heard of that before?
Wait, how did you get all that from a bunch of colored squares?
I'm not saying he's right. I'm just bringing up what he's talking about.
Dude, how did you get all that from a bunch of colored squares?
My range is bigger, I don't know.
Blue and yellow. And
I know
then
a
you
relation,
got
though.
a bunch of leaded squares.
He's relating it back to that, but I'm not saying that this is a Fibonacci pattern. Okay? So look and check. Like, could we do that? I don't think so. But it's a cool that you're trying to connect that. And we're going to come back and I'll talk about this in a minute. This sequence, hey, listen please. You can actually use that, like if I said this and you would be really mad if I asked you to do this by hand. X plus 2 to the 4th would be like a lot of work just by hand. X plus 2 times X plus 2. And then that result times X plus 2. And again, X times X plus 2. But it's called binomial expansion. And we can actually use the Fibonacci sequence to tell us the coefficients of the terms, which is cool. Maybe someday when we get to that, I will show you that. Anyway, good job, Jack. Let's look at just row 2. This row right here. Do you see a pattern in the numbers in that row?
Skip 1 every time.
Which means it's doing what?
Um,
Don't overthink. If I say 1, 3, 5, 7, 9, what are we doing each time? It goes up by 2 each time, right? Good.
Exactly, but.
no, you don't get it on the door.
So
Okay.
if we're adding 2 every time, what kind of relationship is that? Raise your hand on this. If we're always adding the same number,
So linear function.
it's a linear relationship, right? So every time in the row number we add 1. So this should look familiar, especially after your quiz on Friday. We add 1 to each number in the numerator, or in the top rather. And then here we're adding 2 each time. Okay, so what would we call that if I said write this as a linear equation? What would you call that relationship? The what? Up 2 and up 1. Up 2, up 2. That's the slope, right? It's the slope. So if I said write a linear equation, again, just for these top 2, if I said write a linear equation, you would see the change in y each time is 2, the change in x each time is 1. So it would be our slope. Everybody see that? Isn't it interesting how when we pull that title off of something and I don't say, hey, write a linear function, and I don't say, hey, write, find the slope, that now when it's framed as patterning, that it gets a little confusing. Did anybody notice that happen? Like, what's the pattern? Wait, that's just slope. Okay, well, at least for this it is. Is the bottom linear?
No.
So the total? Does it have a constant rate of increase? Well, we started here by adding 3, and then we add 5, and then we add 7, and we're just adding the second row to it, but it's not linear, is it? No. What does linear mean?
You keep adding the same thing.
A straight line.
Constant rate, straight line, constant slope. We're changing in a constant way, which sounds kind of weird, but that is the case. So just to clarify, we had a quiz on functions. Like, is it a function? What's the domain and range of the function? Our quiz was on, can you write a function rule from a table or from a graph, which meant finding the slope and the y-intercept. And we had it as plug in, or find the slope, plug in a point, and then convert it to slope-intercept. Okay? We also did evaluating functions. So I'll just write one up here, like f of 2. If I gave you a function rule, let's say it was 2x squared plus 10x. Don't shout this out, but what is f of 2? Please. Don't shout it out. Just raise your hand. I'll call on you. I'm going to move that while you're thinking. What is f of 2 for f of x given there? All right, I have a hand up, 2 hands. Let's go. Let's get everybody. What is f of 2? Okay, that's better. We're getting a few more. 5 or 6 now. Keep going.
I have a question.
In a second. Keep going, keep going. Okay. Tell me what you got.
36. 36, yeah.
Okay, and remember that f of 2 means plug 2 for each x in the function. That means it looks like this. 2 times 2, so we plugged it in there. 2 squared, and then 10 times 2, we plugged it also in there. So 2 times 4 is 8, and then 10 times 2, you guys told me 36, it should be 28.
2 times 2 and then 4 squared.
No, that's the wrong order of operations. You got to do exponents first and then multiply, right? In other words, square, then times 2. So that becomes 8 and then 28. So we did that, function evaluation. That was 3, that's the first 2 sections in Unit 3. We're skipping 3.3, so we're not doing that section. And now we're jumping to this. This is the same unit as that stuff was. Even if it doesn't seem like it, it is. And that means that this kind of stuff will be assessed with the other stuff later on. Okay? Any questions on what I just told you? Okay. This section is about what we call arithmetic sequences or patterns. Okay? And arithmetic just means that it's linear. Grab your notes. We're going to start defining a few things.
Oh, there's a huge line.
Yeah, I put it there.
Wow, that's pretty crazy. So what are we doing now? Oh, sequences.
Do I really need to always keep my eye on you? I mean, I can better up here. If you'd like. Okay. Okay. Guys, a sequence in general is just a series of numbers, often formed with a pattern. Not always. So in general, a sequence is a series of numbers. Often they're formed with a pattern, but not always. So I mentioned a second ago we're going to talk specifically about this word. Now, say that word.
Arithmetic.
Arithmetic.
Oh, arithmetic.
I know, it looks like arithmetic, right? But we use it as an adjective instead of a noun. So, arithmetic sequence. Arithmetic.
Metic.
No, arithmetic.
Medic. Like a dog.
Metic. No, it's a T. Arithmetic.
Arithmetic.
What's the
The
difference
doctor
between
is med with a D.
I know, but it sounds like D when you put it all together.
met?
Oh, well, okay.
Metic, like
This is math, not conflict.
me
Focus
and
on the numbers, not the
and
letters.
take like the bug.
Well, it is important.
Well, actually, you do need to focus on the letters.
Guys,
Let the
we
man
could
talk.
all do the math.
He's right, though. We're actually going to write about some letters. We do need to focus on them,
Oh
too.
my God. I want to go home.
Get this to us.
Don't we all? All right. So this is now a specific type, right? A specific type of sequence in which the values change by a constant amount. That sounds kind of strangely what? If something's changing by a constant amount, it sounds strangely like a linear function. Yeah. Okay. That constant amount has a name, and this time, or in this, it's called the constant difference. What was the constant difference in the pattern for the fabric for each row? What was it?
Oh, 2. Oh, up 2.
So each row, we were adding 2 more shaded squares, right? So the constant difference was 2. 2 shaded squares for each row. Guys, we're switching the name just for this analysis purpose because our brains are created to see patterns. And specifically, we're calling this now an arithmetic sequence or pattern. But this is just a linear function. It's just a linear relationship. Okay?
I have a question. Constant difference. Where it's constantly changing, like from.
So we also have geometric sequences, which, guys, when you hear geometry, you think like shapes. A geometric sequence is actually a constant multiple instead of a constant difference. Like we're multiplying by 3 each time. Definitely not linear, but it is constantly being multiplied by 3. Okay? All right, this is going to be some new stuff, and it hopefully isn't a big deal because we've done a little bit of it before. But in terms of notation, so that we can interact with this, we are going to be using subscripting to note which term we're talking about. Okay? So we call those terms, successive numbers in the sequence. And so we use subscript notation. Now we've seen this when we, let me wait till everybody writes and I'll show you.
And that's like putting like a number or another letter to the lower right of the.
Yeah, you got it. Don't write this because it would be confusing. But we've seen this before. Here's what I mean. We did y minus y sub a. Subscripting that a told us that's the y coordinate of the a point. Okay? And then we went on and said m equals mx minus x sub a. Okay? So that's subscripting. We also did that in our slope formula. So we had ya, actually it was yb minus ya over xb minus fa. You're used to seeing it in those contexts. Okay? That was subscripting with the letter saying, hey, these are 2 different points, points A and B. We're just making sure we're clear which one we're talking about. Okay? For this, it's going to be the same position, but now we're going to use a little different in terms of what we put down there in the subscript. It'll be a little different. So, A is what we're going to use for each term that we're talking about. Okay, A sub 1 represents the first term in the sequence. Which kind of makes sense with the 1 at least. Okay. A sub n. By the way, this is really common beyond just this application, but using n to represent which term we're talking about goes through lots of different maths than just algebra 1. So this is going to be weird. It's going to sound weird. just go with me on this. This represents the nth term in the sequence. Okay, let's finish that thought. I'm just kind of waiting for you to stay caught up. Hold on. Remind me at the end, okay? At the end of this. Where n is the term number. Okay? Let's pause there and do a quick example. If I have a sub 20, what does that mean?
The 20th term in the sequence.
Yep. That's just the 20th term.
Can we write this again?
Yeah, I would, in the sequence. Okay? So maybe we're talking like in the fabric example, a sub 20 would represent how many shaded squares are in the 20th row. So way down there, right? I think ours only went to the 5th row, so this would be 15 more rows down. How many shaded squares would there be? Okay, that's what the sub tells us. All right. This makes a lot of sense, but it looks a little confusing. So just let yourself process it for a second. So a sub n minus 1. And this is how we say these subscripts. We say sub, not subscript, but just a sub. Okay? N minus 1. What do you think that means? If n is the nth term, what would a sub n minus 1 be?
Negative
No. Good thought.
one, down one.
Yeah.
It would be the nth term down one, yeah.
Yeah, the term right before that, right? So if we use our example from before, a sub 20, what would be a sub n minus 1? If n is 20, then that would be the what term? 19th term, okay? So this, we're going to describe it this way. The term right before the nth term. Okay, again, I think an example would help. So
like 19.
if we say a sub 20, it was a to the n. Actually, let's do it this way. If n equals 20, then a sub n minus 1 is the 19th term. The one right before it. Okay. In our fabric example, we went up to row 5, and it asked in the table, one of them was like the 4th row. So what would be the a sub n minus 1 of that situation? That would be the 3rd row, which I think had 5 or something.
I have a question.
Go ahead.
Is this leading to like equations inside the sub?
No,
Oh.
there won't be any. He's asking, will there ever be an equation inside there? There will not.
Okay, that's good. I was
Yeah,
getting concerned.
probably. Yeah. All right, so this is how we notate. You're going to see these things in our formula for a arithmetic sequence. Okay, this is why we're talking about them. Each of these things will show up in the actual formula. Okay, don't write this, but here's what I mean. This is kind of a formula for a line. Do you agree? Y equals mx plus b.
Yes.
And now everybody in here knows what each of those 4 things tells you. We're going to have that same kind of idea for arithmetic sequences as well. Are we ready for an example yet? Okay. Let's just start by answering whether or not it's arithmetic. Don't shout this out. Just think of your answer, and then I'll say, everybody tell me. So is that list, does it represent an arithmetic sequence? Go read your definition again if you need to. Can you quit? Okay, raise your hand. Or no, don't raise your hand. Give me a thumbs up or down. Is it an arithmetic sequence? Okay. What did that go up by?
13.
What did that go up by? Okay, etc. So yes. What is the constant difference?
13.
Remember we wrote that in our definition?
13 over 1.
13. It's just 13. If we're thinking of it as slope, it would be 13 over 1. All right. Next one. Don't shout it out. It's just this first one here. Okay, is that a arithmetic sequence? Everybody give me a thumbs up or down. What's the common difference?
7.
No, it isn't. Is this going up by 7 every time? Oh, so it's negative. Good. Okay, go ahead and do those two, and then we'll check both. I'll just pause here for a minute or so. He's already gone, so you just can wait. You'll have to wait till break. Like till the bell, I mean. 25. Well, by the time he gets back, it probably will be. Okay, that's probably enough time. How about this first one? Is it an arithmetic sequence?
Negative 7.
Okay, what'd you say it is?
Negative 7.
Okay, how about the next one?
Yes.
Yeah. Negative 6.
Yep. And the common lift is negative 6. Negative 6, negative 7.
Okay,
Can we get an example of one that isn't one?
sure. Okay, is that a arithmetic sequence? Why not?
Because it starts going down by 10 and it goes down by 5.
Okay, so we have those couple values that foul it up a little, right? Good. All right. So questions on arithmetic sequences. Okay. Let's look at how we're going to write them, huh?
Darn, all my principles are.
So it looks kind of weird. Everybody take a second to look at it. Don't read all the words. I'll tell you what they'll say in a second. But just that's our recursive formula for an arithmetic sequence. What do you think? Does it look kind of ugly? Okay. Guys, recursive, you can read this, but it just means to do something over and over again. So if we want to generate this series of numbers, if we just think about a machine that like runs stuff through over and over again, that's what this is doing. Like we take our value, plug it in, get a result, and then we drop that and go to the next term and do it again. Okay? So let me explain what this is saying. Now we know what a sub 1 means. That means it's the first term in our sequence. The nth term, we know, is whichever term we care about. Maybe it's the 10th term. So we take the 1 before it and we add the common difference. Okay? So if we go back to these examples, let's look at that. What is the first term in this sequence? What would a sub 1 be? Okay? What was our common difference? -7. So the nth term would be the previous term minus 7. That is a recursive rule for this sequence of numbers. Here's what I mean. Let's see if I can get it there. Okay? So take this first one. Okay? That would be, let's actually start on the 60. Okay? Take the previous term, which is the 67 value, and subtract 7, which gives us the nth term. I know, you guys, you gotta get over the 6, 7 thing. It's just... Okay, let's go to 53. So that's the third term in the sequence. So a sub 3, the third term, take the second term, which was 60, and subtract 7. And that gave us 53. Okay, the fourth term in the sequence. So a sub 4, take the third term, that's 4 minus 1, take the third term, which was 53, and subtract 7, that gave us 46. Do you see how this works? It's just like repeating it over and over. That's what recursive means.
So, my question is, if you subtract more than 1 from an, does every time you add another subtraction of 1, do you multiply d by another factor? Like, an minus 2 is plus 2d, and then...
Yeah, we don't do it that way, but yes, that's how it would work. Good job for thinking of that. Okay, how about this one? How do we generate the fifth term in the sequence? So our recursive formula, we start with, what is our first term? 80, but how do we get the fifth term? Based on this little description we wrote. So the fifth term, I'll write it this time. So a sub 5 equals what? Fifth term. A sub 4, which is the fourth term. And what was our common difference in this one?
6.
Okay, minus 6. Does that work? Well, let's see. Take the fourth term, 62, and subtract 6, we get 56. That's the fifth term. Okay? Now, this is a little bit of a pain because what if I said the 30th term? What would you have to do? Using this, what would you have to do?
You'd have to work all the way to 30.
Say it again. Listen over here.
You'd have to work all the way to 30 from the original.
Fifth.
Thank you.
Right? You'd have to get the 6th, the 7th, the 8th. Recursive means do it over and over. How boring would that be? Right? Do you see a limiting use to this? Like the 30th term. Oh, I got to know the 29th. To know it, I got to know the 28th, etc. What a pain. Grab your notes again and let's write the recursive formula.
This pen's. Oh, God.
Okay, so just writing what we just talked through. The nth term is the previous term plus the common difference. But make sure we say all that on here.
W teach.
What are the homework questions?
Okay.
What are the homework questions?
I'm gonna tell you. Hold on.
Oh,
I was just seeing where if we. I think that's probably good. All right, circle these, please, or mark them somehow. Number 12. Number 14. 17 to 24. So that whole section. And that's probably good right there.
Thanks.
Number 7. 1, 29, 43, 57.